Good afternoon and welcome to this new edition of this cycle, The Future to Come. I'm the director of the TV series, The Brain Hunter. I'm going to introduce the mathematician and the speaker this afternoon, Marcus du Sautoy. And after presentation, we will have a Q&A session, and I will be able to moderate a debate that I hope is very productive, very fruitful among all of you, those attending through Twitter or through the streaming, or anyone that can pose a question. Then we will have someone who will explain a little bit Marcus' book. But what we cannot know talks about the limits of knowledge. And I remembered an anecdote in the TV series that I'm in charge of. We visited the CERN in Switzerland, and there was a physician in Spanish physics, which is said that knowledge is like an island in an ocean of ignorance, and the borders are what we do not know, and there are several islands of knowledge. And what happens is a paradox, because as we create knowledge and we make our island bigger and bigger, the borders are also growing. So we increase the feeling of ignorance that we have. So what Marcus proposes is, shall we reach at some point in time a moment where these islands will start to meet each other, and we will reach a point where we may have all the knowledge that we can encompass? Probably the answer is no, but where are the limits of each discipline? I think that is an intellectual exercise, an intellectual sport that will be very interesting, and I'm sure that this is going to be a very exciting debate, and I hope that we can all take part in it. Sandra Hoyo, the editor, will make a presentation, a more thorough presentation of Marcus and his work. Or the other way around. I was going to introduce Marcus myself. He's looking at me with a weird face. He's a professor of mathematics in Oxford, and he also has a chair of public understanding of science. And I would like to delve a little bit deeper into that public understanding of science and how science reaches society and in what way. And he has also written several books, some of them very successful, like, for example, Symmetry, the Mysteries of Numbers, and What We Cannot Know, the Prime Numbers, and so on. And so I turn the floor over to the editor, Sandra, who will introduce Marcus.
Muy bien, pues muchas gracias.
Thank you very much, Pere, and thank all of you for accompanying us this afternoon. In this presentation, this is the fourth book that we published of Marcus. I think that we can consider this a milestone in his long trajectory, and a very interesting one. It is a milestone because, as the suggesting title refers to, is to unveil that part of knowledge that historically had remained inaccessible to science and to mathematics. That is to say, he wants to cover all those, or to cross all those borders and barriers that every scientist encounters throughout his career. I guess that all of you that know Marcus will not be disappointed by this book. It is very courageous, and for those of you who do not know Marcus, I think that you will be fascinated with his work, as happened to myself, because it is very easy for him to get you involved into the pages and drives you through concepts that are for someone who is not very knowledgeable in science. It is a very interesting journey, and I guess that the talk that he's going to deliver today is going to be like a horse every very interesting one. So I turn the floor over to him. Thank you.
Unfortunately, one of the things I do not know is Spanish. So I will be speaking in English. Actually, it always makes me laugh a little bit when I get introduced and I get given this very grand title, the Professor for the Public Understanding of Science, because it sounds such a grand title, and it gives an audience the expectation that I must know the whole of science, and here I am to explain it to you all. Certainly when I took over this job a few years ago, a lot of journalists just expected that, yeah, I must know it all. So I would get journalists phoning me up, asking me just every question about science. And I remember just shortly after I got the job, a journalist from the Times in London phoned up and said, yes, the Nobel Prize for Medicine has just been announced for the discovery of telomeres. Could you tell me what a telomere is? Now, unfortunately, biology is not my strong point. So I'm very embarrassed to admit that I was, in fact, in front of my laptop and I quickly pulled up the Wikipedia page to telomeres and read to the journalist, it's the bit at the end of the DNA which tells how long the cell lasts, and the journalist seemed happy with this, but it made me realize, well, there are limitations to my own knowledge. I can't know it all. In fact, who was the last scientist that knew all the science that was known at that time? Maybe Newton? Galileo? But the explosion of knowledge from Newton and Galileo and their generation means that science is just too big for any one scientist to know it all. But it got me thinking, might there come a point when science might know it all? Might there come a point where science has answered all the questions about the universe? Or maybe there are some questions out there that by their nature we will never be able to answer. I mean, the universe surely has not been set up as a kind of exercise in the history, philosophy of science. It would be very anti-Copernican if we could know it all. Somehow that would be very strange. So I went on this journey for the last few years, looking at all of the sciences, trying to identify whether there were any questions that we may never be able to answer. Not that we can't answer now. Sure, there are lots of things we don't know, but questions that by their nature we may never be able to answer. And my journey, which culminated in this new book, the journey takes me to 7 what I've called edges of knowledge. 7 areas that I think might have limits to what we as humans can know about our universe. And I want to take you during this conference on a little journey into a couple of them to give you a feel for what we might not be able to know. I think that desire to know is very basic in us. It's almost part of being human that we want to know. Those who wanted to know survived in this world. Those who didn't want to know died off. So it's part of our evolutionary makeup. And I start the book with a quote from Aristotle, who said, "Everyone by nature desires to know." So I think it's almost part of being human that we want to know answers to things. It's helped us in our evolutionary journey. But I think it's very dangerous for any scientist to stand up at any point in history and say, this is a question we will never be able to answer. Because that's like a red rag to any scientist. Any scientist is going to say, well, I'm going to prove you wrong. So I kept in mind a few examples through history of people who said, well, we're never going to be able to know this. One of my favorite examples is Auguste Comte. Auguste Comte, a French scientist, declared in 1835, we shall never be able to study by any method the chemical composition of stars. And you might think, well, that's fair enough. You know, how can you go to a star, dig a bit of it out, take it back to the lab to see what it's made out of? I mean, we still haven't visited even our own star, the sun, to take a piece of it away, to analyze it. But what Comte hadn't taken into account is that although we haven't visited a star, Well, every night the stars visit us. The light from the stars comes to us, and several decades later, scientists could analyze that light, and we now know very complete description of what stars are made of. So, very dangerous, I think, to say we cannot know this. But I'm raised as a mathematician, and I thought maybe I could use my mathematical mind to analyze a question to see that by its nature it's something we will never be able to answer. Now, I'm not the first to consider the idea of the unknowns. Many people have talked about the unknowns. One of our great 21st century philosophers, Donald Rumsfeld, made a very curious statement about unknowns. This was a response to questions about weapons of mass destruction during the Iraq War. The journalists were rather perplexed when Donald Rumsfeld replied, there are known knowns. There are the things that we know that we know. And we also know that there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. Those are the ones we don't know we don't know. And the journalists were like, what sort of response is that? We want to know whether there are weapons of mass destruction. And he got given the Foot in the Mouth Award by the Plain English Speaking Society for this response, which I think is very unfair, because I think this is a beautiful description of different states of knowledge. The known knowns. That's what we teach our undergraduates at university, the things we do know. And the book is very much about the things that we know, how that knowledge has changed. How does knowledge change as we go into the future? How do we discover new knowledge? How do we know that we know things? So the known knowns are very much at the heart of this book, because by knowing how to discover new things, it can help us to go into the unknown. The unknown unknowns. Well, I can't tell you about those, obviously, because they are unknown. But these are very important. If anyone's read Taleb's book, The Black Swan, these are our black swan events in science. They're exciting. The things that we can't predict. Someone like Albert Einstein appearing, who completely changes our perspective on the universe. Scientists love these moments because they are game changers in the history of our subject. I'm after the known unknowns. Now, there are lots of things we know we don't know, but I want to see, can we identify things that will always remain unknown, that will always be beyond us? Actually, I think that Rumsfeld missed one category. What about the unknown knowns? And actually, as Slavoj Žižek pointed out, these are very important for a politician, because they're kind of like the things that you deny that you know, but they're kind of like your Freudian drives, they're your delusions, the things that you don't want to know about, but actually are part of who you are. I think, for example, Donald Trump has a lot of these unknown knowns that drive him. But anyway, so we're after the known unknowns. Is there anything that we can't know? Maybe we can know everything. One of the other motivations for this journey into the unknown was partly the person I took over this job from, because the person who had my job, the professor for the public understanding of science before me, was a certain Richard Dawkins. Now, Richard Dawkins obviously became very famous for his books on biology, but perhaps more recently, he's become famous for his fights with creationists and theologians. His book, The God Delusion, got him into a lot of feisty debates with theologians. So a lot of journalists, when they phone me up, as well as wanting to know what a telomere is, were also quite intrigued to know what my religious beliefs were. Was I going to be a militant atheist like Richard Dawkins, or perhaps I was going to tread a different path? I was quite keen to put a bit of distance between me and Richard and to talk more about science rather than religion. So I told the journalists, I am in fact a deeply religious man. Now, the journalists were slightly shocked by this, a scientist declaring himself deeply religious. But then I went on to explain that my religion is the Arsenal Football Club. So every weekend I go to my temple, I worship my idols, my football players, we sing songs to them. Every season I reaffirm my faith. This is a season when we're going to win the Premiership. But like any good religion, my faith is tested again and again, so we still haven't won anything. But anyway, so this... some journalists were happy with this, but others said, no, surely you can say, are you an atheist or religious? And after a while, I decided actually to engage in this debate, because in some ways religion is after the same big questions, trying to answer the big questions about where we've come from. Why is there something rather than nothing? What's it all for? And so after a while I did engage in some debates with some theologians. In particular, I did a debate with the chief rabbi in London, who wrote a wonderful book actually called Science and Religion, The Great Partnership, which talks about the fact that science and religion is interested in trying to answer very similar big questions. And in preparation for that debate, I talked to a philosopher friend of mine at my college in Oxford, and he recommended a very interesting theologian from Oxford called Herbert McCabe. Herbert McCabe, he's a Marxist theologian, which I thought was quite a cool combination. But he wrote a lot of essays about Christian liturgy, which are very obscure and strange, but he wrote a few which actually resonated with me. And in one, which is called God Still Matters, he makes this assertion. He says, to assert the existence of God is to claim that there is an unanswered question about the universe. Simply that. And actually he goes on to say that we have committed idolatry, really, by giving this very abstract concept far too many properties it never should have had. We give it a personality, a history, and in fact, it's a very abstract idea which is quite hard to wrestle with, which is why we give children a kind of strange version of this. So I thought, let's take this as a definition on my journey into the unknown and see if God is just a question that there is an unanswered question. Can science say what that sort of God would be and what sort of influence it would have on our universe? So one of the strands in this book is also looking at a kind of theological debate about the unknown and its impact on us as humans. So let's plunge into some of these unknown questions. The first edge I want to take you to is actually an edge which is very close to my own subject of mathematics. And this is the question of whether we can know the future before it becomes the present. I think as humans we spend a lot of time thinking about the future. It's one of the qualities of consciousness, I think, that we can do mental time travel. And one of our best tools for trying to predict what might happen in the future is my own subject of mathematics. Actually, when I tell people I'm a mathematician, I think most people think I'm doing long division to a lot of decimal places, and surely my computer's put me out of a job. But actually, a mathematician, I like to define a mathematician as a pattern searcher. That's what mathematicians do. We try to look for patterns in things that have happened in the past, and by reading those patterns we can take the pattern forward into the future and hope to know what might happen next. But how powerful is this tool of mathematics really to know what's going to happen next? Now, on my journey to each of these edges in the book, I took an object with me, something tangible that could help me to try and explore this question. And I think somehow the ultimate symbol of the unknowable, of the unpredictable, is a dice. The reason we find a dice so fascinating is that if I throw this dice, there seems to be no way to predict how it's going to land. So let's throw, this time I got a 2. but surely mathematics can give us the tools to be able to predict this dice. I certainly thought so. I spent a lot of time learning the great work of Isaac Newton, who gave us the laws of motion which dictate how this dice falls from my hand, how it lands on the floor. He invented the calculus, which helps us to understand a world in flux, a changing world. And surely those tools could help me to predict that this time we got a 6. Well, I went off to Vegas, and I thought, having spent all my time at university learning these tools, perhaps I could have an edge and I might make some money. Unfortunately, I lost a lot of money, but they let me keep the dice. So this is the dice we used in Vegas that day when I lost all my money. But how unknowable is this? Surely Newton has given us the tools. And certainly scientists post-Newton believed that now we had the equations, the tools to be able to predict the universe, that it was just a piece of clockwork machinery, that if you knew how the universe was set up now, you run the equations and you can know what's going to happen in the future. Now, if Newton is my hero in this story, then this guy here, Henri Poincaré, is the nemesis. Because Henri Poincaré showed that, okay, sure, if you know exactly how the universe is set up, you can predict the future. But we had this intuition that, sure, I can't get an exact description of the universe, but I can get a very good approximation. Now, the thought was, before Poincaré, that a good approximation of the present, you run the equations, and you'll get a very good approximation of the future. But Poincaré showed that this intuition was false. Just a very small error in a description of the present can cause a completely different prediction for the future. And this is the discovery of chaos theory. Chaos theory, its discovery in the 20th century, really places limits on the knowledge that we can have about the future, even if we have the equations to be able to predict those, the way the universe evolves. Now, I have here one of my favorite examples of chaos in action. See how stable this is. So I'm going to put it, let's put it here. Because you might think, okay, complicated things like the weather, sure, we can't predict those. But this is a very simple thing. It's a pendulum. Pendulums are so simple and predictable, we use them to keep track of time. It's one of the things Galileo discovered. But this is a slightly different pendulum. This is two pieces of metal joined together a bit like a leg. And the geometry of this is very straightforward. The mathematics of it. The physics, also very simple. It's just gravity. This thing is practically frictionless. So the physics is very simple. But trying to predict the behavior of this thing is almost impossible. Ooh, let's see. I think that's losing a lot of energy. Let me try it up here. I need something very stable because the energy gets lost. So. Right, can you see that? Well, let's see. So trying to predict this thing, wow, whoa, look at that. That's a, wow. You got one more? Yes, yes. Now, I think the fact that some of you are even laughing at this is an indication of the unknowability. I'll do the other one over here so you get a look. Now, in fact, it's quite good that I'm repeating it because one of the points about chaos theory is that it's very difficult to repeat the behavior. Now, I had a little mark here, which is where I start this thing off. So I'm going to try and do the thing in the same way as before. So let's set it off. Whoa. Now, it's starting off very similarly, but if you on this side, it went a lot of times. Oh, let's see. I'm going to try that one again. Let's see. Wow, great. Yes, you see, it is just so funny because you can't predict it. I mean, actually, this is my favorite desktop toy. I can play with this for absolutely hours. So we'll do one more here over here. Let's see what. Whoa. It's just crazy. So we know the equations for this, but to be able to predict this behavior, you've got what? Whoa, that's fantastic. Wow, he's really showing off now. Yeah, he's got going. Now, I have another example of chaos in action, which is this little... it's another pendulum. This has 6 magnets, and the magnets attract the pendulum. In fact, each of the magnets has an answer to a question over the top. So I actually use this to make all my decisions in life. For example, you ask it a question, and it'll answer definitely, no way, try again, ask a friend, yes, maybe. Okay, so Arsenal are playing Moscow on Thursday in the Europa League. Should I put a bet on Arsenal winning on Thursday night? So let's so we'll set this off and see what it does. So I've got a little example here. You try and predict. This is a pendulum with 3 magnets. You try and predict which magnet you think the pendulum is going to end up at. The thing is just as crazy as my pendulum. It looks schizophrenic. Just doesn't know where to end up. Is it going to be the top right-hand corner? Right at the end, it pulls to the bottom magnet. Let's see, what oh dear, it says, no way, make a bet. Oh dear, that's my faith tested again. So this thing's always right as well. So this is 3 little tests I did, where I started the pendulum off in this top left-hand corner, and now I've coloured the magnets yellow, blue, and red. And when I first set the pendulum off, it landed at the blue magnet. Then I changed just the 6th decimal place of one of the starting positions. You can barely see it starting in a different position. It starts off fairly similarly, but then quickly goes off somewhere else and ends up at the red magnet. Then the 3rd experiment, I changed it just a little bit again, and now it ends up at the yellow magnet. So incredibly difficult to predict. And here is in fact a diagram which helps you to know what this pendulum is going to do. How do you read this diagram? If the pendulum starts over a red region, that means it's going to end at the red magnet. Now the red magnet is somewhere in here, so if I'm very close to the red magnet, of course the pendulum will just wobble and the other 2 magnets aren't strong enough. So there it's very predictable. I can know what it's going to do. There's another very predictable region which is opposite the red magnet. There a small change doesn't alter things much because it just swings backwards and forwards and ends at the red magnet. But I started my pendulum off in the top left-hand corner. This is an example of a mathematical shape called a fractal, which some of you might have heard of. A fractal is a mathematical shape which has infinite complexity. As you zoom in, it does not simplify. You might think as I zoom in, it's suddenly just going to become yellow. So I know that now I can predict this thing because I got to the 7th decimal place. But as much as you zoom in, you will always see red, yellow, and blue regions. It never simplifies, such that even a change of the 50th decimal place will mean that it can change from a blue to a yellow and end up at a completely different magnet. So this diagram shows you that mathematics can have regions where you can know, but sometimes these equations are too sensitive, and then you have to throw up your hands and say, now we do not know what is going to happen with these equations. Now the trouble is that these equations control many things we would like to know about in our lives. It controls the weather. I mean, did we know 2 weeks ago it was going to be raining in Madrid? I wouldn't have taken up the offer if I knew it was going to rain. Have enough rain in London. But and that's the trouble. The weather, very good predictions for 5 days, but by the 6th, 7th day, a small change in the weather today can cause a very different prediction for the weather in 2 weeks' time. So the weather, the economy. And in fact, I took with me, as well as an object, a person to the edge of knowledge. So the person I took with me to the edge of the world of the chaos was this guy here. This is Bob May. He's an evolutionary biologist, and he understood that many biological systems have chaos inherent in them, which is why biology is such a difficult subject actually to know about. But he's now working with the Bank of England, trying to understand whether the economy was also in a chaotic region when we hit the banking crisis in 2008. And he's working in the House of Lords with Parliament. He's working with MPs. He is a Lord himself. I went and had lunch with him, and he made this comment over lunch. He said, not only in research, but in the everyday world of politics and economics, we would be better off if more people realized that simple systems do not necessarily possess simple dynamic properties. And I think this is one of the problems with politicians, is that they expect scientists to know it all. And they don't understand this subtlety that sometimes a system can be so chaotic that we can't know what it's going to do next. I asked him how he was getting on teaching the politicians some mathematical chaos theory and calculus, but he said, Marcus, they're mostly interested in their egos, not in higher mathematics, unfortunately. Now, I wondered whether maybe the reason I can't know what this dice is going to do next is because it's chaotic. But I got a little bit of a shock. This dice is not as unknowable as you might think. I discovered a piece of research done by some Polish mathematicians who show that there are times when you can know what this dice is going to do. Just like the pendulum, we can know sometimes which magnet it's going to end up at. Now, they did some very high-speed camera capture of the dice falling on the table, and I'm going to show you some pictures similar to the picture I showed you for the pendulum. So I've coloured the dice with red face, yellow face, green face, blue face, and I want to be able to predict which colour will appear on top of the dice. So these are the pictures that they discovered. These are 4 different sorts of tables you might meet at a casino. Now, the tables you want to play on are the tables corresponding to this picture here. This picture here is fractal. The one in the bottom right-hand corner is fractal. It means a very small change. So what are the parameters here? I'm measuring what the distance above the table is and the angle that the dice is leaving. So this table here, a very small change in the height or the angle causes the color to completely change. So these tables are one a bit like this floor, which is very rigid, and the dice bounces a lot. So here is one of the reasons we can't know what the dice is going to do. These are the tables you want to play on, because a very small change in the height, if you're in that yellow region, a small change is not going to change it. It's still going to land on the yellow side, or a small change in the angle. So what tables are these? These are tables of casinos that are a little bit old, bit down on their heels, they're a bit soggy, and somehow the thing doesn't bounce too much. And actually, if you take one thing away from this talk, hopefully 2 things, a book and also this fact, it turns out that more often than not, the dice on these tables lands on the face which is face down on your hand when it leaves the dice's hand. Now we can do a little experiment here. This looks quite soft. Yeah, this is a very soggy table over here. So so we're going to do a little experiment here. So it's a 6 here. So I'm going to just let it fall, and there. You saw it was a 6, so it did land on the face that was face down. So that's amazing. Big round of applause for that, because that doesn't usually happen. The experiment works 1 in 6 times. So anyway, so that's a little journey into the. Yeah, somebody got the joke there. So I'm going to take a few more minutes, if that's okay, to take you on a journey into another of the edges. An edge which actually is this discovery we made in the 20th century, because everything I've been talking up till now has been very classical 19th century physics, very deterministic, but in the 20th century, Einstein and his contemporaries discovered that unknowability is at the heart of the way we must do science. And this is the topic of quantum physics. Quantum physics says that unknowability is actually just part of how we must do science. So the object I took with me on my journey to the edge of the quantum world was this pot of uranium that I bought on the internet. It's amazing what you can buy on the internet these days. So, this pot of uranium, I managed to get this past airport security, which is pretty impressive this afternoon. Now I've let I probably won't get back to London, but so what's interesting is this number on the side of the pot, 984. That tells me how many bits of radiation are being kicked off every minute. So if I open, I probably shouldn't do that, sorry. Blow up Madrid. So this says 900, over 1 minute, 984 bits of radiation are being kicked off here. What this can't tell me, it seems like what physics can't tell us, is when it's going to do that. This is on average. On average, the dice lands 1 in 6 times on the 6. On average, over a minute, 984 bits of radiation. But physics cannot tell us, and physics says there's no way to know when it's going to do that. Now, actually, you can write these. If you look on Amazon, you've got wonderful reviews. I love this review that somebody made. He gave it a 5-star, said, "So glad I don't have to buy this from Libyans in the parking lots of the Mall anymore." There was another review, somebody gave it just a 1-star, and said, I had this for 5 billion years and it's half empty. Which is the Half-Life joke, so anyone who laughs at that. Good, so at the heart of this unknowability is this thing called Heisenberg's uncertainty principle. And Heisenberg articulated in a mathematical formula that there are things that we cannot know about our universe. In particular, if I want to do Newtonian physics, I see an electron flying through the air, I need to know its position and how it's moving, its momentum. Heisenberg said you can't know both of those things. That the more you know about where the electron is, the less you can know about how it's moving. You might say, well, I know where it is now, so now I'm going to measure how it's moving. But it turns out the more you get information about how it's moving, you have to give up knowledge about where the electron is. It starts to be able to be spread across the universe. So you seem to have this trade-off, and it's in a mathematical formula. It's not some fuzzy thing. These are the errors. The error in the position, as that gets smaller, the error in how it's moving has to get larger. You give up knowledge. So I'm going to give you a little test now. Okay, I'm going to tell you my favorite physics joke, and if you laugh, you understand Heisenberg's uncertainty principle. So Heisenberg is bombing down the motorway in his BMW, and the policeman pulls him over, gets him out of the car, and he says to Heisenberg, "Sir, do you know how fast you were going?" And Heisenberg goes, "No, but I know exactly where I was." Okay, yeah, good. Some good laughs there. Those of you who are sitting there saying, I don't understand why that was funny. Or maybe you're having to wait for the poor interpreter, who I apologize because I get very excited and talk very quickly, and he's probably pulling his hair out there. So, why is that funny? You should never have to explain a joke. But the point is, because Heisenberg knew where he was, he had to give up knowledge. His speed could be on a whole range of things. When he's looking at his speedometer, it suddenly becomes very fuzzy. Okay, so here's a follow-up to the joke to see whether I can get more people laughing. So the police officer says to Heisenberg, "Well, you were going 200 kilometers per hour." And then Heisenberg goes, "Oh, now we're lost." Good, that's good, yeah. Because they know more about their speed, they have to give up knowledge about their position, and they don't know where they are anymore. When we come to questions, there's a third bit to the joke, because Schrödinger was in the back of the car. But actually, this is the heart of why this thing we can't predict it, because I know a lot about the atoms, the particles inside the nucleus, about how they're moving, which means I know less about their position, which means the position can be outside the pot, and I get radiation. Now, actually, I'll skip over this. Einstein believed that this unknown would not be one that would be there forever. He believed that surely there must be some mechanism that will help us to predict this. And he made this very famous statement. He said, "Quantum mechanics is very impressive, but an inner voice tells me it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice." But if you talk to any physicist today, they will say that this is just the way the universe works. But I don't think that's going to... I'm a little bit with Einstein here. I think that we will eventually find some reason for how we can predict this. We know from the physics that it's going to be a very bizarre mechanism. You might think, oh, maybe there's a little clock inside the atom. But we now know whatever mechanism it is must be spread across the whole universe, which is determining when this thing will radiate. But ultimately, I think this unknown, although it's part of science today, I think it will... that we're waiting for another black swan event, another Einstein, and maybe one of the young people in this room will be the person who will overturn our complacency, our kind of satisfaction with this theory, which almost works too well, as Einstein says. It's very impressive, and it is very impressive. But my belief is that scientists have kind of given up a bit too early, and I think this won't be an unknown that will remain there forever. Well, that was a little journey into two of the unknowns. Perhaps we can talk when we discuss a little bit more some of the other unknowns, whether the universe is infinite, what's going on inside our heads, consciousness is another one, the nature of time, and mathematics itself has unknowables. But I think on that note, I will end and open up for a discussion and hopefully some good questions from you too. So thank you very much.
I was finishing the tweet about your joke.
Oh, okay, right.
The Heisenberg. Yeah, I was definitely tweeting this. In fact, if anyone who's watching, perdón, si alguien que nos está viendo.
If anyone who is watching us through the streaming wants to send a question for Marcus, they can do it through our hashtag Futuro por Venir, and I will deal with 3 topics. I'm not going to ask him questions, proper questions, but discuss a few topics, and then we will turn the floor over to you. Marcus has opened up many areas. It's like a mixture of science and philosophy. When I was reading the book, I was amazed at your approach. I read in that is there anything that we cannot explain or understand, or I want to know whether there are things that by their own nature we will never be able to know. I'm a biochemist, and as a biochemist, perhaps some of you will say it's of course there are things that we will never be able to find out about or get to know what is happening in nature or in our brains. Do you think that this approach, that this hypothesis, so to speak, that I'm not saying that we will get to know everything, but do you think that it is more of an approach of a physicist or a mathematician, not so much someone of other disciplines?
Experiencing what you did of this delay. I think it's very interesting, this difference between a subject like mathematics, physics, and your messy subject like biology. But when I was exploring this, I felt that biology probably has a lot of things that we will never know, but that they aren't essentially things that we can't know. I mean, there's complexity issues and mess, and partly the first edge, the chaos edge, is talking about biological systems, and the limits of a very small change can cause a completely different animal to evolve. And the question, for example, in evolutionary biology, whether if we ran it again, would we get the same animals? Would we get humans again? Is one of the big open questions. But I felt that didn't have the same nature of unknowability as some of these questions in physics, for example. So something like one of the edges I talk about whether we could ever know the universe is infinite. Now that seems, if it is infinite, how could we ever know because information travels at the speed of light, maximum speed it can go, we know from Einstein. So the universe has only been going for 13.8 billion years, so that means that we've only received information from a certain bubble around us. And how can there's no way we can know anything beyond there. So that seemed a different quality of unknowability that is almost an essential unknowability, whilst biology, although there's a lot of mess, it's a complexity thing which by its nature doesn't mean that we could not possibly know. For example, you might be able to run evolution again and discover that, yeah, we do get convergence. For example, many species evolved the eye in many different ways, but somehow this mechanism of evolution always gives us eyes. But will it always give us cats, for example, or are cats something special for this particular run? So it's interesting. I think because I'm a mathematician, I want to identify questions like, you know, if you think my colleague in Oxford, Andrew Wiles, proved Fermat's last theorem. He proved that this equation cannot have solutions. We know that there are no numbers which will solve this equation. And I think I was hankering after questions that I could categorically identify as unknowable, rather than just saying these are messy and complicated. But there's nothing essentially unknowable, I think, about many biological questions.
Depends. Depends on the data that you have. O sea, claro,
if the universe is infinite, when you were explaining it, I interviewed Alan Guth in the MIT, and he was studying whether the universe was infinite through mathematics. And the origin of the universe, which is one of the big mysteries, how this did everything start, perhaps mathematics and some evidence of the Big Bang and so on that reaches us, that could perhaps lead us to have some sort of explanation about how everything started. But the origin of life, we don't have any data about that other big mystery. How did life on Earth emerge? We can create possible scenarios that comply with the laws of biology, but because of that lack of data about that period, that is not something that perhaps we will never get to know, how life started in life.
A lack of data is not an essential unknowability, because there is a potential that that data might appear. So the fact that we don't have the data now does not means that we can't know now, but we might be able to discover new evidence of fossils. We might meet alien culture. I think that will be one of the black swans that will happen, is that we will encounter another place which has run evolution, and so we will get more data, because we will see that they've got cats as well. So there's probably something essential about cats. Whilst I think that actually cosmologists, it's very interesting, because cosmology works on an important concept called homogeneity. And in fact, one of the big questions in the book is about consciousness. Is your consciousness anything like my consciousness? Well, yes, I believe it is, because you're very like me, so it's very likely that your consciousness is similar to mine. Now, we apply this in physics of the universe, that we believe what our universe is like here should be very much like the universe anywhere. But that's not absolutely clear. We could find that when we go over some horizon, that the curvature could change dramatically. For example, if we're on the surface of the Earth, there's no reason why at some point it couldn't have gone flat. We could have been living on a hemisphere. The surface, so suddenly this curved space becomes flat. Now, the universe might be like that. So all of these physicists who are talking about the possibility of proving the universe is infinite are working on a fundamental assumption which could be wrong.
Yeah.
And they can't know, because you cannot know something new happening beyond that horizon.
Interesting. Quiero abrir.
I would like to open up a new subject. You mentioned in your presentation, you mentioned religion. And in your book, you mention religion as well. I'm very interested on the different viewpoints that different scientific disciplines have about the world. In the case of religion, we know, because there are data, that the scientists tend to be less religious than non-scientists. And within scientists, the physicists are normally a little bit more religious. Why is that? Why do you think that happens?
This is very interesting because I had 7 edges and I talked to 7 different scientists, and I was quite surprised at how many of them actually did have some religious faith. But I think that there are 2 different sorts of religious scientists. There are what we call the deists and the theists. Now the deists will say, look, I don't know where all of this stuff came from. I don't know what the creator is. So I'm going to call that thing God, which created this thing. But now the universe follows laws, and I'm going to be a scientist and I'm going to study those laws. I think Einstein was a little bit like that. He used God a lot in his discussion, but I think God was a placeholder for the fact that he didn't know why there was something rather than nothing. So I think a lot of religious scientists are of that ilk. I think more interesting are the religious scientists who actually believe their God acts in the world. And actually the scientist I took to the edge of the quantum world was a scientist called John Polkinghorne, who's a quantum physicist who trained with Dirac, Feynman. You can't ask for better teachers than that. But halfway through his career, he decided to become ordained as a priest in the Church of England. And he is a theist. He believes his God is acting in this world, changing things. So I went to talk to him because I wanted to know, as a scientist, how is that working? What is the science that you're using to explain the action? And I wondered, as a quantum physicist, was he going to use the kind of unknowability of quantum physics? Because as humans, you know, if an electron could be anywhere, I observe it, and then it makes up its decision where it is. And that seems to be totally random. But maybe that's an expression of his God acting in the world, that although we as humans cannot know it, that actually something external is making those decisions, which we can never know. But he didn't use quantum physics. He actually used chaos theory as the way his God was acting. That humans can only know a certain amount about our universe, and that in the decimal places you can sort of tinker with the universe and make it do things which humans will not be able to observe. And it's interesting because Isaac Newton, he was a very religious scientist. He also believed that his God was acting by changing small things in the universe. And of course, chaos theory means that small things can result in very big outcomes. But his great rival Leibniz said, but I don't understand, why wouldn't God have set up the universe to be perfect in the first place? Why would God need to keep on tinkering with it in the decimal places? But it was very striking. And so your question about why physicists, exactly, I think cosmologists perhaps are the most religious. So in the chapter about whether the universe is infinite, I interviewed John Barrow, a cosmologist in Cambridge, and I know him very well, and I got a bit of a shock when I asked him. I assumed he might be agnostic, but he said, no, I'm a deeply religious person. And partly it is because of the wonder at the universe and the kind of there's so many things about cosmology that will always be unknown. And he sort of felt that biology was a much more knowable and tractable subject, which is perhaps why the likes of Richard Dawkins, you know, we've given an explanation. We know how animals evolve. We know the mechanism. It's, you know, it's evolution, and Darwin has explained that. What we don't know is how the universe evolved. The constants of nature, the weight, the mass of an electron, the mass of a proton, they're so finely tuned that just a small change in one of them would mean that the universe could not have evolved. And so one of the big questions in the book, actually, is, okay, why is our universe so perfectly set up? It seems like, you know, one explanation is that there is a designer, somebody who's dialed all of these things up so it's perfectly tuned to create life. Scientists at the moment, the only other explanation we have is that there are perhaps infinitely many other universes. This is the multiverse theory. And in each of those universes, the constants, the mass of an electron, a proton, are being randomly assigned, and we just happen to be in the one. Of course, life could only evolve in the one where things were perfect, but there are many, many other universes where these constants are in different positions. A bit like, you know, why is the Earth perfectly in the position for life to evolve? You know, Mars isn't, Jupiter isn't, the Earth is in the Goldilocks area. But there's no reason for that. It's kind of random. And there are loads of planets where life cannot evolve. So now we believe the universe is similar. That, but you know, is that any... We will never know about these other universes. We're stuck in our own universe. Yeah. And that is a very big theme in this book. The problem about being stuck inside a system and not being able to get out of it. It's the problem of consciousness. Consciousness, we're stuck inside our heads, and there's absolutely no way I can pull myself out of my head and get into your head. And this problem of being stuck inside a system, I think, is fundamental to many of the unknowns in this book.
Permíteme que profundice.
Allow me to delve a little bit deeper into that relationship between religion and science and the frictions that sometimes happen or take place. It is quite evident in your book and also in your career, professional career. I like that distinction that you made between religious scientists that propose two different things. One thing is my experiment, my worldview, and then where I cannot reach, there may be a God, and those that try to fit it together. That would be the scientist that you mentioned, or a very well-known example is Frank Tipler. Frank Tipler, do you know him? He is trying to fit together Christianism. I think that is cheating. Intellectually is cheating, trying to fit in science to explain God. And I would like to know your opinion about that. But on top of that, being a professor of the public understanding of science, we know that one of the missions of the scientist is not only to explain what science does, but sometimes also to fight pseudo science or semi-sciences, or to correct those mistakes that we all believe in and that go against what science says. And Richard Dawkins, that you mentioned, has been quite active fighting religion. I'm asking you several questions at the same time, but do you think that is one of the functions, one of the missions of the scientists, to be constantly in that friction with religion, or should we leave religion to our beliefs?
I think that what Richard did was very important, because, and especially because of the situation in America, where there's a fundamental attack on education of science, in particular talking about the science that he's involved in, evolution. However, I think that this debate got too polarized. And I think that this is, what often happens in these debates. You need to have this, a big fight to mark out the lines. But I think that too much was thrown away. And I think that, I do declare myself an atheist. That is a decision about, I've made a decision about something I can't know. But I think, again, as a mathematician, I need a very good definition of what God is, and very often there isn't a good definition. And I thought that this definition that Herbert McCabe gave was a very good one, and I think it gives us a more nuanced debate about religion, because what was religion? It was always meant to be the things which transcend our knowledge, and that transcendence very early on was about not understanding nature. Volcanoes, earthquakes, they were acts of God. Now we understand the physics of those. So I think that there's a more nuanced discussion to have, which is why I think that I took in a sense, a brave decision, as you said, to write this book, which is trying to actually just not ignore what the theological side has to say, but is there anything that science can usefully add to this debate about transcendence? Are there things that we can identify that are unknowable, which might be an important ingredient in a theological debate? Of course, I do think that most of religion, as Herbert McCabe said, has committed some sort of idolatry. It's necessitated taking something very abstract and making it, going against the whole spirit of that definition and giving it tangibility. Well, as soon as you make it tangible, it's suddenly invalidated the definition. So I think that as I said, science and religion have been trying to deal with very similar big questions. So I think it's inevitable that we will have a debate, but I think it's important that we don't become entrenched in these polarized views, which are not giving us some healthy, interesting engagement.
Yeah. Yo le vuelvo a preguntar.
Well, I'll ask you again, as a professor of the public understanding of sciences, about the boundaries, about the limits of knowledge, human knowledge, science limits. And you quote them in the book as singularity people, Ray Kurzweil, people that define that this growth, this exponential growth of knowledge and technology will take us to immortality, to colonize other planets, to upload our brains in the hard disk of a computer. Is it a techno... Well, it's an overstated techno-optimism. At least that's my opinion. We have to be very critic as journalists with this. What's your point of view of this phenomenon that, well, it's going through its way, but now it's very strong here in Spain? We have people that appear on the media quite often saying incredible and crazy things about the future of the marvelous future that we'll have. I mean, what's your point of view about all these things?
It's interesting this is called the singularity movement, as you mentioned in your question, because singularities are things in mathematics beyond which you cannot know. For example, the Big Bang is a singularity, a moment when we cannot know what happened before the Big Bang. But actually, I think that that maybe we can know more about what's going to be beyond this moment when technology somehow overtakes us in what it can know. And I think that there are a lot of scary movies at the moment which somehow frighten us about the power of the machine if it becomes too powerful. I think we have to recognize that probably this is just part of evolution. That this is the next stage in evolution. That in some decades' time, these machines will be coming and visiting the zoo, and we will be behind bars, and they will be saying, look, this is what we evolved from. So I do think that we have to recognize that we're probably a transition stage on the way to another species. And what will be interesting is when we meet alien life, which I think we will do, probably not in our lifetimes, but because I believe that that alien life will not be biological, it will be silicon. And I think that the consciousness chapter deals with this in some extent, because you know, I believe that you're all conscious human beings. I mean, some of you are looking a bit zombified, I must admit, sort of, which is fair enough. We've been pushing you hard. But, you know, I don't believe that any of you are genuine zombies, that there is no internal world going on. But I think, you know, how many of you got smartphones in your pocket? The question is, you know, you've got an iPhone, let's put a hand up there, you know, when is that thing going to become conscious? That's a very important question. You know, if suddenly your iPhone starts going, iPhone think, therefore iPhone am, you know, are we going to have to give it rights? How can we tell that moment when the network has become so somehow complex that it is actually past a threshold, which is presumably what's happened with our network inside our brains. So I think that you know, that is going to be a very important moment in in talking about future technology. And the book talks a lot about how we can know whether a piece of technology might become conscious. Weirdly, it turns out that mathematics might have the answer to this, that we might have an equation which can tell whether something has become conscious or not, which will be able to measure an iPhone and say it's got some small level of consciousness. Or even an audience. You see, we're a network. We're a networked, you know, you're listening to us, you're all sort of plugged in. When you go to the theatre or you go to a concert, there's a kind of collective consciousness which starts to emerge, which is about a network of people coming together and sharing something. There might be some way to measure that and say, yes, it's not as conscious as you are, but it has some level of consciousness.
No, definitely. ¿Alguna pregunta?
Is there any questions from the audience? We have one at the back. Yes, please. Well, first of all, thank you very much. And secondly, I would like to ask you about energy. Physics says that energy is neither destroyed nor created, but it is transformed. So, I would like to know what's your opinion about the energy that we have when someone passes away. What happens with that energy?
It's a great question. Well, of course, Einstein, first of all, you know, his great equation E equals mc squared shows that we have some movement between mass and energy. And so, but we can have negative sorts of energy as well. So one interesting theory that I came up throughout the book was that the universe actually started from, you know, why is there something rather than nothing? Big question. Big open question. But this one explanation is that actually we started from nothing, but that in some way, the same way that 0 can become 1 plus minus 1, from nothing you could get something and a negative, and that actually the whole universe, if you looked at its collective energy and mass, that it has in fact 0 energy and mass. But in some places you see a positive example, and other places a negative example. So that's a very interesting thing. But you referred to what happens to somebody when they die. Now, I think that we already know that, you know, perhaps you get cremated, the atoms change, they move away, they go blown in the wind if you're scattered on a mountaintop, or maybe they're buried in the ground. So the actual particles that are you are still all there, they're just in different arrangement. Now here's the interesting thing. There is a theorem in physics which says that no information is ever lost. This says that although you burn something, there's still all the information there to recover. Now I can burn a copy of my book, but all the information is there to recover that information. So Polkinghorne, the physicist I talked to who's religious, believes that this allows a possibility for reincarnation. Because the information that makes you who you are, the way the atoms are collected together now to create a network in your brain, even though you die and you get perhaps cremated or buried, that information is never lost. It's very hard to recover, just in the same way as a burnt book. It's very hard to put together. But the physics has a theorem which says that information about who you are is never lost. The only place where it might be lost is in a black hole. And of course, this is one of the things that Hawking had a big bet on, about whether black holes actually, he believes that the radiation he posited that black holes are radiating, that radiation contains the information of what went inside the black hole. But others, like Roger Penrose, my colleague in Oxford, he believes that black holes actually can kind of destroy information. And for him, that's very important. We have this thing called entropy, which is that the universe is getting more disordered. Entropy is increasing. Why was the universe in a very low state of entropy and it's getting bigger? He believes that black holes are a way of resetting the universe to a low entropy setting, but that necessitates a loss of information. And in that case, if you're cremated by being put in a black hole, we might lose who you really are. I'm amazed. I think we should give a round of applause to our signer, because I've been really pressing our signer for.
Voy a dar más preguntas
Okay, so we'll make more questions. Marcus will sign his books. I would like to answer that question as a biochemist, but well, the energy that we have is the energy that we generate with our breathing, when we breathe oxygen, and after that we have just some atoms that are, that microorganisms use, of course. But well, another question there. Yeah, please. Yeah, that's good.
Thanks. I'm really liking your talk. I think it's very well explained, so really enjoying it. Thanks. And given what you've discussed so far, I wanted to ask you your opinion about the simulation hypothesis stated by Nick Bostrom. And he basically says that there's a possibility that humans evolved eventually enough to create an artificial simulation for the universe, life, for everything. So we would be trapped into this simulation and would never know that we are simulated, and would never know what's beyond.
Yes, I think he goes even further to suggest that there's a very high probability that we are in the simulation, because if we, surely we will evolve to be able to simulate. We can already simulate black holes on this thing, so why can't we simulate a universe? And then, there's only one universe, but there'll be many simulations. Now, I think there's actually a proof that we are living in a simulation. The proof is that the Americans elected Donald Trump and the British voted for Brexit. This simulation has gone badly wrong, and the person who started running this simulation has said, oh, bugger this, and has just let the computer run, and we're having to experience what these things are like, and they're on to the next simulation where they've actually retuned the thing, and they haven't elected Donald Trump, and Britain is still in Europe. But I think there's a more interesting point, obviously, than this, which is that this was the ultimate criticism of the skeptics. Is that, how can we know that we're not just brains in a vat being fed information, and that, like the Matrix, how can we know that we're not living in the Matrix? And of course we can't know that. But I think that my answer to that was, I can't know that we might not be living in a simulation, but what can I know about this simulation? So the best that we can do is to know about the simulation that that's either running on our brains or that we are stuck inside, and that's the best that we can do. And it's similar to the best that we can do is to understand the universe that we're stuck in. There may be another universe with different physics, but we were never going to know about that. The weird thing is that are we starting to create stories in science which are frankly not scientific? If there are multiverses, and this is our best explanation for why the universe is tuned like it is. We can never know. It seems like we're never going to be able to know that. So that's not testable anymore. So are we actually starting to create stories which are as fanciful as religious stories? Now, I would say that there's a difference here, which is that there's a kind of sense of economy, the kind of Occam's razor, that you want your explanation to be as simple as possible. Now, you might say creating infinitely many more universes is not simple, but at least we have one example of such a universe, so maybe there are infinitely more. Creating a God who tuned things is making something completely new, which I have no evidence for. So I think our explanation, although it may not be technically testable and scientific, is still a good explanation, better explanation.
Pregunta allí.
Encontramos la...
We find mathematics in nature. What comes first, nature or mathematics? Who creates mathematics? The humankind discovers mathematics?
This is a perfect question. I could almost planted that question. You see, one of the big questions is where all this stuff came from. And if you're trying to answer that, you need somebody to create that. And that's why religion produces the idea of a creator. But then, you know, as my kids say, well, then who created the creator? And you start getting into this. Now, the interesting thing about mathematics is that you don't need a creator. Mathematics is outside of time. Mathematics didn't have a moment when suddenly it was created. Certainly it has a moment when it gets discovered by us as humans, so that feels often like a moment of creation. But it's my belief that mathematics is outside of time. It has always been there. It's a nature of the relationship of structures. So for me, one of the ultimate conclusions of the book was that, of the theological strand, is that if you're after something to explain why there is all of this stuff. You see, there's so much mathematics explaining everything that many people say, well, if there is a God, then God is definitely a mathematician. I would reverse this. I would say, no. The point is that the God you're all after is mathematics. Mathematics is the God. Mathematics is, I would say this, I'm a mathematician, but mathematics is the thing which led to the creation of everything we see around us. Mathematics is outside of time, and what we have around us is a physicalized piece of mathematics. And this is sort of why we're seeing mathematics everywhere. It's not sort of being created by us and our viewpoint. I think the mathematics is there because the mathematics gives rise to structures. A little bit like, you know, 0 is equal to 1 plus minus 1. So there's a possibility of nothing becoming something and a negative. So it's something that Max Tegmark, who you might have interviewed for your program, Max Tegmark is also a believer. He's a physicist, wrote a book called The Mathematical Universe Theory, I think. He's also a believer in this idea that the reason we see so much mathematics around us is because we're living inside a piece of mathematics. And actually, I spent some time in Bhutan, and I spent some time talking to some Buddhist teachers there. And Buddhism is actually has very similar sort of ideas in its theory of cosmology, which resonated very much with the way that I was thinking about mathematics and its place in the universe. So,
Creo que tenemos que ir.
I think that we have to finish, but we'll make a very brief question and a brief answer, okay? It's a very brief question. It's about the 6th border. I'm still at the 4th one, but it's a very simple question. Do we have, are we free or not? Does freedom exist, or are we determined? I mean, our consciousness lets us be free or not? That's a big question of the consciousness. That's simple.
Yeah, so this is a question that I deal with in the book because it's such a good question. And in fact, it's a good question for the two edges that I talked about. Because if we're living in a deterministic Newtonian physical world, then we don't have free will. But that doesn't mean that we don't have the illusion of free will. And I think that's what very often we're talking about, is that because we can't, chaos in some sense gives us that illusion that we can't really know what's happening and we feel like we have control. However, quantum physics perhaps allows for free will because if you run an equation in quantum physics, an electron goes through this slit or this slit and you can never know where it's going to end up. Maybe humans don't have free will. The only thing which really has free will is that electron that's using quantum physics. So maybe on the very small, that allows some freedom to creep in to counter the deterministic universe that Newton would say. But I'm actually a determinist at heart. I think that quantum physics thing will, you know, if we were here in 100 years, we'll find that there's a deterministic system controlling quantum physics after all. So I don't believe in free will. I think it's just an illusion. You thought you had free will coming here tonight? It was all determined. I knew you were all coming here.
This physicist, as a biochemist, I un último comentario.
No, just a last remark. I have to say this because reading his book, I've remembered a very famous physicist that passed away a month half ago, Jorge Wagensberg. Some of the things were recalling that constantly because, well, he reflected about the boundaries of knowledge. And there was a story that you've mentioned football, and you've mentioned that there are some problems that seem simple, and they're not, and other problems that are more complex and are simple. And I was quoting chess and football. Chess really is really simple because there's a specific number of moves. Of games. I mean, there are not infinite games, but football is unpredictable. And he's really speaking about Heisenberg, the undetermination principle, with the chaos theory. And he says, well, if we go back with evolution and we start again, maybe it will be the same again. That recalls me football. I mean, a slight change in that first shot, for example, could take to a game to a different result, to a goal or whatever. And there are laws, of course, evolution laws. But in my case, I have the feeling that our knowledge is much more limited than what we think. But you have the last word, okay?
Well, maybe my last word will be the third part of the joke. Do you want to know what Schrödinger?
Sure.
Yeah, sure. Nobody asked about Schrödinger. Okay, so I'll tell you the last bit of the joke. Schrödinger's cat is this hypothesis that if an electron can be two places at the same time, then a cat can be alive and dead at the same time until you observe it, and then it has to make up its mind. So that's all you need to know for the joke. So the policeman goes round to the back of the car, flips the boot open, and goes, "Oh, you've got a dead cat in the back of your car." And Schrödinger says, "Well, it's dead now."
Well, it's a great... Buena manera de terminar.
It's a great way of finishing this. I think that we have, well, now we can buy and he will sign the books. Thank you very much, Marcus, and thank you very much to all the audience.
Gracias.